Hello and welcome to seminar of supercapacitor usage in modern electrical utility systems. My name is Mohammed Mohiuddin and I am an applications engineer at Eaton Corporation. Jason Lee is our global product manager for supercapacitor. Today's agenda for this presentation is brief introduction of Eaton Corporation, present few issues of power grid systems and possible solutions using supercapacitors, supercapacitor technology and advantages of using them, Eaton supercapacitor products, and finally, the resources at your disposal. Let's start with Eaton Corporation and who we are. These are the latest available financials from 2021. Within Eaton Corporation, which had $19.6 billion revenue, electrical sector accounts for $12.7 billion. It is the global sector within Eaton Corporation. Hydraulics, aerospace, vehicle, e-mobility are other industrial sectors. Our heritage. It all started with axle manufacturing in 1911. Over the years, Bussmann, then Cooper, Magnum, Qualtronics, and PowerStore became part of Eaton Corporation. Then in 2012, Eaton Electronics Division was formed. Supercapacitor business, which is the topic of today's presentation, came from acquiring PowerStore in 1911. Eaton is a global corporation. Our manufacturing plants, regional offices, R&D facilities, and distribution centers are located around the world. To diversify manufacturing, plants are located in China and Philippines. More manufacturing locations are being added. Electronics division is made up of magnetics, circuit protection, supercapacitor, terminal blocks, and the latest addition of sensors. Magnetics generates the most revenue, and circuit protection being the second. Supercapacitor is relatively small business, but the fastest growing business within electronics division. Computing, industrial, and automotive sectors are our biggest market verticals in terms of revenue. This brings us to the beginning of our core presentation. Any power distribution system faces several challenges to keep the power flowing from the source to the consumers. This affects the load as well as the generator. Some example of these issues are transients caused by frequent power cycling. Grid disturbances transpire when power production is not matched with demand. For backup power or storage batteries, frequent power cycling reduces published capacity. This published capacity of battery is reduced significantly when energy starts to flow out beyond its prescribed limit, however time limited the event is. And finally, the reliability is affected by unforeseen events, such as mechanical breakdown, system faults, human errors, etc. These issues are not exclusive to any one type of distribution systems. For example, transients, disturbances, or reliability manifest to the traditional power grids as well as microgrid system. Let's discuss the issue of transients and finite power. It is a common theme across the globe to reduce the dependencies on non-renewable or hazardous energy sources, namely fossil fuel or nuclear power. It helps reduce carbon footprint and production of unintended hazardous byproducts which are difficult to store after the useful end of life. Hence comes the need for the wind, solar, and hydropower plants to fill the energy gap. Unlike the traditional hydro or nuclear power plants, renewable energy power plants are distributed throughout the region. However, these relatively new types of power plants have limited and inconsistent power production. Whenever there is inequation between the load and the source, disturbances show up on the grid system. Traditional power plants are not immune to these disturbances either. To overcome these unwanted events, operators of these plants increase or decrease the power production. One method is using peaker plants, which are special gas turbines. However, these peakers are expensive to operate and inefficient. Other methods may be employed to overcome these issues. Because of the inertia due to their enormous size, it takes time to spin up or down the generators, the traditional power generators. Distributed or small production facilities have limited or inconsistent power output. A few reasons are partial or rolling overcast over solar farm, unsteady wind speed at wind turbines, seasonal changes in water flow for hydropower plants. Unlike traditional power plants, which have too much inertia due to their size, distributed power plants do not have enough inertia to keep the grid power steady. More challenges. Electrical circuit powers either resistive or reactive loads. Resistive loads such as heater or incandescent bulb do not cause phase shift between voltage and current in an AC system. However, reactive loads such as motors or transformers cause a phase shift between voltage and current in an AC system, which in turn creates power factor issues. Any load generally does not operate continuously, either resistive or reactive. For example, a heater or air conditioner may react to environment and cycle the power, creating transient issues. On top of the transient problems, reactive loads cause phase shift and either consume more power or produce phantom power. So the question is how to intelligently and efficiently solve the issue we just presented. First graph in the top right corner simulates power demand, while the second one next to it is excess power, which is mostly wasted. Graph 3 at the bottom is the suggested solution utilizing supercapacitors. Supercapacitors can help the peak demand from its reservoir and capture the excess power whenever necessary. Challenges with opportunities. Whenever there is a challenge, there are opportunities. In this challenge, supercapacitor is the most cost-effective energy storage option. A bank of supercapacitor can yield power from fraction of second to tens of minutes, or capture energy that is wasted in the form of heat. Smart grid solution devices such as STATCOM is becoming more popular to regulate line voltages. It reacts to the demand and supply and helps maintain the grid voltage to the regulation levels. Static synchronous compensator, or STATCOM, are used in high voltage DC systems. For the power systems operating between 11 to some 50,000 volts, enhanced STATCOMs maintain active power requirements. It is becoming a requirement in Europe, Middle East, and Asian countries. North America is soon to follow these requirements. This slide represents an example solution for the distributed power system, which is output firming. In this example, a bank of supercapacitors using 380 of Eaton's XLM modules is configured to operate for 60 seconds, providing 1 megawatts of power. The graph in the upper right corner shows the characteristic discharge curve for voltage and current. The graph on this slide is constructed using real-life data. Blue trace is the scheduled demand, while reddish-brown trace is the actual demand. Interesting to note that green trace at the bottom of the graph is traveling across 0-watt line, evidently capturing the differential energy between demand and supply. Coming to enhancing the performance of existing systems. Transporting goods via sea routes accounts for 80% of the worldwide trade, according to the United Nations Conference on Trade and Development, an intergovernmental organization. Port of Los Angeles shipped 10.7 million containers in 2021. Port operators add cranes to keep up with ever-increasing demand. Additional cranes stress the existing grid system. This situation becomes even more demanding when multiple cranes operate simultaneously to speed up the loading-unloading process. This problem is twofold. How to react during power consumption when crane is picking up a container, and when power is regenerated when container is lowered. Regenerated power is traditionally not captured and lost through braking mechanism. One way to solve this problem is to upgrade existing power generation system. However, it is a costly proposal which is also inefficient and does not provide a mechanism to capture regenerated power. A typical seaport consumes 3 to 8 megawatts of power, while grids are capable of providing 4 to 6 megawatts of power to them. Supercapacitors are ideally suited to solve both issues. Grab and store the braking power and release it during peak demand. The supercapacitor bank design faces two challenges. contribute to peak power demand, and capture regenerated energy as much as possible. The solution revolves around the location of the supercapacitor bank, whether to balance a full port or a substation. For the scenario mentioned in the previous two slides, this is an example solution, namely peak power shaving. It saves on capital investment and can be retrofitted to existing facilities. This example solution uses a bank of 399 Eaton's XLM modules, which can run for 20 seconds, producing 4 megawatts of power. Here is a proposed solution for downsizing the diesel engine. The saving in this case are manifold: fuel efficiency, less maintenance, and longer lasting solution, etc. A bank of 105 XLM modules produce 850 kilowatts to stabilize a 900 volt DC rail system. Let's talk about more regenerative energy, but this time for enhanced safety and better system reliability. Continuing our discussion with similar theme, but for a different market segment, this time for electric rail system. The braking energy from train is approximated to be 500 kilowatts for 60 seconds or some 30 megajoules. A bank of 154 XLM modules are capable of storing 33 megajoules of energy, and the solution can last over 10 years. So why bring supercapacitor into an already complex system? Same reasons. Cut down the peak demand and capture regenerative energy from the braking system. The benefits are numerous: 20 to 30% energy savings, lesser additional infrastructure, prolonged components life, safety by moving the train to safe location in case of abrupt power interruption. Optionally, the energy from one train can be transferred to another if mains power is interrupted. The stored energy can be utilized for public safety, such as powering elevators, escalators, and lighting. And in case the same source of energy can be used to recharge the electric vehicles connected to stations' chargers. Showing here is the simulation of capturing the regenerated power from the train braking system. Using the design criteria mentioned on the previous slides, that is, 500 kilowatts of power is available for 60 seconds from the braking. A bank of capacitor made up of 154 XLM modules can be topped off in 60 seconds. It is the 75% of the total capacity of the bank. We have been talking about supercapacitors, but how are these energy storage devices built and what makes them stand out amongst the peers? Here is a refresher. I'll highlight a few key points here. Number one is the double layer of charge that is formed at both electrodes, thus gives supercapacitor higher energy densities. No chemical reaction takes place during charging or discharging. These are electrostatic processes. These have virtually unlimited life cycle compared with batteries. This can be discharged to 0 volts without causing permanent damage. In their discharge profile, voltage reduces linearly while current is constant. On the other hand, lithium-ion batteries are asymmetric devices, meaning the two electrodes are different. Charge and discharge are electrochemical processes. Their life cycle is limited to a few thousands due to chemical degradation and oxide buildup on the electrodes. Their discharge profile is flat, delivering constant power, which is an advantage. In the mix of new storage technologies, hybrid supercapacitors or lithium-ion capacitors are the new entry. These are asymmetric devices where one electrode is doped in lithium-ion. Life cycle reaches 500,000, and there is still no issues of thermal runaways since no metal oxide is used in the construction. This table shows comparison of different storage technologies. I will highlight a couple of points. The initial cost is mentioned as 2 to 3 times of lead acid battery. This cost is coming down. The biggest drawback for supercapacitor is the energy densities, which is only 2 to 10% of lead acid batteries. However, supercapacitors make up for not having higher energy densities by providing enormous amount of power, which no other storage technology can beat. I like to use the analogy of two sports to brighten up the concept of energy versus power. The two sports are American football and European football or soccer. Both have few similarities, such as 11 players per team, and the objective of the game is either place the ball in between the opponent's goalposts or cross the goal line. In American football, offense and defense team have two different sets of players, 11 each. Offensive players do not play in defense and vice versa. During a set of plays or downs, offensive players of one team play against the defensive players of the opposite team. Each team uses ample energy for each play trying to stop the opponent. Their power is unmatched and their performance is analogous to supercapacitors. The regulation time of the game is 60 minutes, but the game lasts for about 3 hours. In contrast, 11 soccer players of each team play for the entire 90 minutes of the game, with only 3 substitutions allowed during the entire game. Their endurance is unparalleled and their performance is analogous to battery. Another advantage of using supercapacitor is their enormous life cycles. Properly designed supercapacitors can last up to 1,000,000 cycles. Let's talk about some more advantages of using supercapacitors, which are long life cycles, numerous charge and discharge cycles, virtually maintenance free, and simpler monitoring electronics design are some of the key advantages of using the supercapacitors. Not to mention the wider temperature range for harsh environment and eco-friendliness are also favorable characteristics of the supercapacitors. What type of supercapacitors Eaton offer for your design? From smaller coin cells to cylindrical single cells, small modules to large modules, hybrid technology cells, and system cabinets are all offered from Eaton Electronics. Few of the supercapacitor offerings are shown here. Please visit eaton.com/electronics for complete product details and data sheets. These supercapacitors are being used in computing, transportation, energy, industrial, and medical fields. In summary, Eaton has a full line of supercapacitor modules with superior performance for a broad range of environments. Modules are configurable into higher voltages to meet design requirements. Eaton supercapacitors provide low total cost of ownership for backup applications, peak power, and energy cycling applications. And finally, the resources. Supercapacitor Resource Center has white paper selection guides, technology comparison, user guides, and many videos. The first link on this page is the landing page for supercapacitor. This presentation will be available shortly after this session, and all the links in the document will be active. More resources and tools are presented here. It covers other products from Eaton Electronics. The 3D virtual display boards are very useful and popular. Please visit these links to experience yourself. This concludes our presentation. Thank you for your time and participation.